Hi everyone. Let's say I tell you to draw 3 cards from a standard deck of 52 cards. Now, you may need to ask me a key question. When you draw the 3 cards, what do you do? When you draw the first card, you look at it, and then you may need to ask what question. Do you put the card back in which case we're going to be sampling with replacement, as we will in this example, or do you keep the card out, in which case we're sampling or drawing without replacement? Let's say in this example, after you pick the first card and look at it, after we all look at it, you put it back into the deck. The deck is thoroughly shuffled. You pick the second card. So basically, as far as probability goes, it's like starting from scratch. The same probabilities apply whether it's the second draw or the first draw. Then after we all look at the second card, you put the second card back in. The deck is randomly shuffled well. You pick a third card and then put that back in. So sampling or drawing with replacement. Every time you pick a card, you immediately put it back into the deck before you pick the next card, if there is a next card. All right. So draw 3 cards from a standard deck with replacement, meaning that after we draw a card, we place it back in immediately before we draw the next card. So if you're going to do this, find the probability that we draw an ace first, a king second, and a king third. In other words, what's the probability that the sequence of ranks we get will be ace, then king, then king? I'll give you 10 seconds to figure that out. All right. What's the probability your first card is an ace? You draw a card randomly from the deck. What's the probability the first card is an ace? Well, what's the probability of getting an ace? There are 13 ranks, each of them equally likely. So the probability of getting an ace is 1 over 13, 1/13. What's the probability of getting a king on any of the draws? So let's say that you get the ace and you put it back in. You get one of the 4 aces and you put it back in. The deck's randomly shuffled. You pick out the second card. What's the probability the second card is a king? Well, regardless of what happened on the first card, the probability that the second card is a king, well, there are 13 ranks, each of them equally likely. Once again, the probability of getting any particular rank, like a king, is 1 over 13. Let's say you get an ace and a king. You put the second card back in. Deck is randomly shuffled. What's the probability the third card is a king? That's still 1 over 13. Now, if we're sampling or drawing with replacement, again, what happens on the first draw, probability-wise, has no impact on the second draw, which has no impact on the third draw. The 3 draws have nothing to do with each other, probability-wise. We have independence. Because we are drawing cards with replacement, the draws are independent. So whether you're picking the first card or the second card or the third card, the probability situation with the deck of cards is exactly the same. There's no memory. So the probabilities involved with one draw are not impacted by the results of other draws. So going by this rule over here, the probability of A and B and C happening, that's P of A times P of B times P of C. We multiply probabilities. So the probability of getting an ace on the first draw and a king on the second draw and a king on the third draw, these could be events A. Don't confuse A for ace here, but the probability of A and B and C, right? Well, the event A does involve an ace in this case. The probability of A and B and C equals the probability of A times the probability of B times the probability of C. We have independence. It's the straight product. It's 1/13 times 1/13 times 1/13, also known as 1/13 what? 1/13 to the third, or cubed. Exponents come up a lot in these independence problems. By the way, that's 1 over 2,197. It's not very likely. It's about 0.000455. For that matter, what's the probability that you get 3 queens? What's the probability that you get a 2, a 3, and a jack? Each of these probabilities will be equally likely. There are 2,197 ordered triples of ranks. Rank, rank, rank. There are 2,197 ordered triples of ranks, each of them equally likely. Each of these ordered triplets are equally likely. It's the same probability. Look at this possibility tree. You have equal probabilities on each of these branches. 1/13 for each of the ranks on the first draw, and then 1/13 for each of the ranks on the second draw, and then 1/13 for each of the ranks on the third draw. Whichever path you take, including ace, king, king, is going to be 1/13 times 1/13 times 1/13, or 1/13 cubed. So for each of these paths, whether it's ace, king, king, or queen, 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 all right, it's going to be 1/13 cubed. It's going to be the same probability. This for all of these paths, for all of these ordered triples. All right. Now, in the next example, we're going to ask a similar question. What's the probability of getting the sequence? But how do you think the problem's going to change? What's going to make this problem more interesting? If you are told to draw the 3 cards without replacement, every time you take out a card, it stays out.